Thank you very much. Moving on. So here's an overview of my talk. I'll start with a brief introduction. I'll talk about various different features of accelerator technology, starting with low energy beams, magnets, RF cavities, wake fields, multi-physics, and a brief look at how you can simulate some of these devices using the 3D Experience platform. There's a few things I'm not going to talk about, for instance, diagnostics, which are also, as Richard referred to in the introduction, frequently modeled using our tools. So moving on to the introduction. So particle accelerators are complex machines, and we've heard about lots of complicated machines already, but you can't really argue with particle accelerators. They tend to be built of modular components, which can include, for instance, for electromagnetic simulation, special apparatus to handle beam creation, magnets to bend, focus, and shape the beam, and cavities that can accelerate particles to higher energy. So we've heard some of these referred to in the previous talks, but with accelerators, they have a special focus. And many of these components may utilize superconductivity to reach higher fields or to save costs. And these kind of components need to be very well understood so that they operate reliably. And if they exceed their superconductivity conditions and undergo a process called quench, that can be modeled and protection built in. And it's also important, as we've heard already, that it's important to simulate the interaction of the beam with its surroundings. So, for instance, particle tracking and interaction, which can include electron cloud, space charge effects, and beam current effects. The specialized example of that of wake fields, but then also multi-physics effects like thermal and stress. And in the picture at the top right, Richard referred to the Large Hadron Collider, and this is the Large Hadron Collider tunnel underneath France and Switzerland. And the blue devices you can see are 15-meter long bending magnets that operate at about 2 Kelvin, and there are just over 1,200 of them in the Large Hadron Collider tunnel. So that's the kind of, which is 27 kilometers round. So from a perspective of accelerators, both CST Studio Suite and Opera actually began through collaborations with particle accelerator laboratories. CST Studio Suite began in Darmstadt, which was near to the accelerator HERA at Frankfurt. HERA was an electron-proton collider, a very interesting machine, and it was one of the first superconducting accelerators using superconducting bending magnets for its proton beam. But it was also essential, CST was also essential for the development of the Large Electron Positron Collider superconducting accelerator cavities at CERN. This was the accelerator that preceded the Large Hadron Collider. And without CST, the accelerating cavities wouldn't have been made to work correctly. Opera came from Rutherford Appleton Laboratory in the UK. It was designed to simulate the first generation of superconducting magnets. But particle accelerator laboratories worldwide use it as a standard now for the simulation of all kinds of accelerator magnets. CST was acquired by Dassault Systems in 2016, followed by Opera in 2018, and both are part of the SIMULIA brand. As part of this incorporation, Opera technology is being brought into the CST front end, and at the moment, the Opera magnetostatic solver is available, but others will follow in the future. So moving on to a brief look at low energy beams. So Richard has talked about some of these in the vacuum electronic devices. Electron beams for accelerators look very similar to the kind of beams you generate for X-rays. However, here's a different kind. This is a Penning ion source. So I talked about a 27-kilometer long tunnel with 15-meter long magnets. Ion sources are tiny things. So this is 30 mil by 25 mil. In cross section. You have a coil to create the Penning field, and then you'll have in this example a hydrogen dihydride neutral gas. We're creating a plasma, as Richard has talked about, and it includes a Monte Carlo collision model with ionization, excitation, and elastic collisions. And by the combination of these fields, you get a positive hydrogen molecule ion extraction, with the color here indicating the particle energy. So we can simulate a variety of ion sources with CST and Opera, and this is just an example. Moving to slightly higher energy, a radio frequency quadrupole is a device that's used to accelerate low energy ion beams from where they're created in something like an ion source to where they'd be injected into a further accelerating structure like a linear accelerator. And what you can see here is the model of this RFQ, and you get the beam injected at one end and extracted at the other. The whole cavity would be resonating with a radio frequency field, and the shape of these undulations along veins or rods in the center provide fields that both accelerate and focus the beam simultaneously. In this plot, you can see the electric field. On the bottom left, you can see the temperature, and the effect of these combined forces lead to a displacement of the veins of the RFQ. So in red, you can see the largest displacement. And then in the right, you can see an exaggerated view of the mesh displacement with temperature laid over it. Moving on to look at magnets. So there are lots of different types of magnets required in a particle accelerator, including bending magnets that steer the beam, focusing magnets that control the beam cross-section, and higher order multipole magnets. So focusing magnets have 4 poles, and multipole, we're talking about things that have 6 or 8 or higher. And these are used as correctors for imperfection in the other magnets or for correcting higher order beam dynamics. And this model on the left is a toy model we've created of an H-frame dipole in Opera, whereas the next one is a real customer model provided courtesy of Jefferson Laboratory, which is a septum magnet, so it's a specialized kind of dipole where the beam would come in at one end and there'd be different kinds of particle in this beam, and they're then separated into 3 separate beams, one coming through the top, one coming through a small hole in the center, and one coming out of the bottom. As I said before, we also need to be able to simulate superconducting magnets. These are needed to achieve multiple Tesla fields. So a steel-dominated magnet can really saturate not far above 2 Tesla, whereas the LHC magnets I showed earlier are designed to run at 7 Tesla. And new generations of superconducting magnet can go up to 10s, 20s, or higher Tesla fields. These can be simulated normally unless they can't be kept below their critical current and temperature, in which case there may be a rapid transition to normal conduction. So there'll be heating effects and a heating wavefront passing through the conductor. And Opera has tools to simulate this superconducting quench effect. And both low and high temperature superconductors can be simulated. And here we have an example of a superconducting dipole. And because the fields are entirely generated by the coil structure, there is often not any steel in these kind of magnets. The most important feature of an accelerator magnet is arguably its field quality. They're designed with specific requirements, and normally for a circulating accelerator, and that requires field accuracy down to 10 to the minus 4 accuracy, so 0.01% in the good field region. So we need tools that can calculate that field quality along the good field region. So for this H-frame dipole, we're looking at a circle through the middle of it, and we track that all the way through the magnet. And then you can use that field quality to modify, parameterize, or optimize to achieve targets. And for instance, one of the key features accelerator magnet designers are looking for are to optimize the Fourier coefficients around this circle. So if we look at them for example, in this plot here from Opera, the dipole term we're looking to maximize is this cosine term here of the 0th order, and we'd want to minimize all the rest. Some of them you can't get rid of completely, but those you'd want to minimize as much as possible. And this is just a small video of a quench occurring in the superconducting dipole I showed you earlier, where you can see the colors, the surface contours on the coils are the temperature, and the vectors are heat flow through the magnet. And you can see that over some tens of seconds, the magnet goes from 3.6 Kelvin everywhere up to 260 Kelvin peak. So it's vital that you handle the heat load and the current loss as the current moves out of the resistive area of the magnet. It's also important to simulate systems of accelerators. So there can be lots of interactions between magnets that are close together. So, for instance, the magnets have fringe fields at the edges that may interact with each other, which may modify their effective magnetic length. You can get saturation effects where the steel becomes saturated in a way that affects the field of nearby magnets. And also they can apply forces on each other and other nearby components. So this is an example of an accelerator I used to work on, the ISIS spallation neutron source synchrotron at Rutherford Appleton Laboratory. And this is a case where you have an H- beam coming in, which is a proton with 2 electrons. It then comes in through a septon, it gets stripped by a stripping foil here, and you can then see the 3 beams coming out. So this is a fully stripped proton beam, which is then going to merge into a circulating beam in the synchrotron. You've got a partially stripped H0 beam and an unstripped H- beam here. And both of these two, the purple and yellow beams, will have to be taken to beam dumps to make sure they're captured properly. And on the right, we've got 2 pictures courtesy of Fermi Accelerator Laboratory in the States of the mu2e experiment, which is generating muons from a proton beam. And it's looking at the decay of muons to electrons. And you can see it's got an exceedingly complicated array of solenoids to handle all of the different tasks that are required for this accelerator. Finally, it's essential to look at particle tracking through accelerator magnets. And in OPERA, as well as in CST, they can be tracked in various ways. Users can define the initial conditions and properties of particles that make up the beam, and space charge forces between the particles can be included. On the bottom left, we've got a model we've generated ourselves of a fragment separator magnet. So in fact, this is only half of the magnet. There's another half here that isn't being shown. And the idea is you've got a radioactive ion beam. Through some collision, you've got lots of interesting isotopes of heavy elements. And what you want to do is separate those out. So by bending it through 180 degrees, a bit like sending light through a prism, you're going to get the different mass states of those isotopes separated out for further study. And then on the top right, we've got another model from Jefferson Laboratory, which is an exceedingly complicated septum magnet with lots of different coils. The steel is quite saturated. You can see the red, you're going up to well above 2 Tesla. And again, we can see some particle tracks going through where we're looking at how that septum is separating out those particles. So that was a brief look at accelerator magnets, and we're now going to go and have a look at some RF cavity simulation. So cavity simulation is essential, and both for calculating the accelerating fields you'll get from these cavities. So RF cavities are used to accelerate particle beams in particle accelerators. It's where the acceleration comes from. And the first state of this is eigenmode simulation to see if you capture the dominant frequencies correctly. However, equally important is from those eigenmodes, you need to calculate the accelerating fields themselves. So you can generate those fields from the eigenmodes once you've calculated them. And then through losses in the surfaces of the cavities and in a variety of other ways, you'll create losses which will lead to heating. So it's also important to calculate the heating effects. And both of those things, the fields which create Lorentz forces which will deform the cavities, and the heating may also deform the cavities, lead to further requirements for mechanical simulation to look at what the effects will be on the cavities. And you can then form a loop where you look at the effect on the eigenmodes of the deformation and try and find some suitable regime of operation to capture all of those effects. And on the right, we have a simulation of one of these eigenmodes in a crab cavity, which is an accelerating cavity that's also used to rotate the beam in longitudinal phase space. And that's courtesy of Dr. Graham Burt at Lancaster University. So 2 of the most important factors involved when talking about cavities are Q factor and shunt impedance. And Q factor is effectively how long the cavity will ring for once you've excited it with a certain frequency. And for superconducting cavities, this can be in the hundreds of thousands to the millions, the Q factor. So they're really very, very efficient. Whereas for something like a ferro-loaded cavity, it might only be 2 or 3. So you've got a huge range of Q factors. And the different things that go into this calculation are the power that is extracted via the coupler, power that's lost in materials coupling that coupler into the cavity, and as I said before, surface losses in the cavity itself. So it's quite a complicated calculation. Whereas shunt impedance is the voltage that's actually seen by the cavity. So we integrate a line along the middle of the cavity where the particles will be traveling, and we integrate the electric field, including the transit time of the particles. And then the shunt impedance is effectively the voltage squared that's been seen by the particles divided by the power at that mode of operation. And yeah, these two things are really the most important figures of merit when you talk about accelerator cavities. So we've talked about multi-paction before this afternoon, and it's equally important for cavities. So as both the particle beams go through and their fields interact with the cavity, as well as just the fields in the cavity itself, you can get an electron cascade where electrons are kicked out of the surface of the cavity, and then if you're unfortunate, they will then bang into the walls of the cavity and kick out secondary electrons. And this can be an avalanche process, as you see in the plot on the right. This can be a process that become dominant and then lead to the cavity no longer functioning as an accelerating cavity. So it's something that you have to prepare for by correct cleaning and finishing of the cavity walls, and by making sure that your bunches are timed so that they let the multi-paction die away before the next bunch comes through. And similar to a multi-paction, but sort of more important, the thing we're most interested in is simulating the acceleration of the particles themselves. So we can do a particle in cell simulation of these cavities where we preload the eigenmode fields. We can choose initial phase and scaling of the particle beam. And for low current applications, you could disregard space charge as well. And as Richard mentioned, there is GPU support. So for a realistic RFQ simulated in CST, you can get a speed up factor of 5 or higher with the right hardware, which, as Richard said, is something to be noted. So what about wake fields in cavities? So there's a very nice animation here of a particle beam going through a 9-cell Tesla cavity, and you can see the extremely complicated wake field that particle bunch is describing. The wake field solver computes the wake potential. It's a time domain solver, and its initial conditions are the properties of the beam. It's suitable for both low and high beta relativistic beams. And what it's calculating effectively, analytically, is if you have one particle at the front of the bunch, what is the effect of the fields of that particle on a particle further back? And again, analytically, what you're really solving is the Lorentz force equation, and you're integrating it over the length of the bunch for the charge. And this is an extremely difficult equation to solve analytically, and it's much better suited to being solved numerically. This is important. The wake field can lead to beam loss. And for example, here is a cavity design from Diamond Light Source, so an electron storage ring. And what they were really interested in looking at was the time integrated surface losses and the material effects on these. They had a power loss calculated analytically via something called the wake loss factor. So here we've got an equation of the power for the charge of the electron squared times this wake loss factor. And CST could include the same value calculated from a monitor. And you can see that the answers agree reasonably well. I think the numerical answer is more likely to be trusted here. And you can also see the power loss over time. And this power loss can then be applied in the thermal solver as a heat source. Equally important to get accurate results is it's important to be able to define the bunch shapes. So these signals can be defined via an excitation function in CST, either by a text file ASCII import or by a formula. So you can see a non-regular shape bunch here, which is important again to get accurate results. So moving on to multiphysics. So here's an example provided by some people we work with at CIMAT in Spain. and it's a 9-cell drift tube Linac structure. So the beam would come in on the right. Again, like the RFQ, this whole structure would be resonating. But in this case, what would happen is while the field was in its accelerating state, the particles would be in the gap between the drift tubes, and it would get accelerated. And then during the decelerating part, it's shielded by these drift tubes. And what you'd like to see is good acceleration of that beam. But for this particular workflow, what we're looking at is a multi-physics workflow, so including both the eigenmode calculation, a thermal simulation, and a particle tracking simulation as well. So if we move to the RF analysis, which in this case is using the lossy eigenmode solver to have an automatic detection of the appropriate eigenmode, and also calculate surface losses in the cavity. So there's a nice animation here showing that eigenmode. And for this kind of solver, you get detailed Q factors, which are available automatically in the 1D results tree. The surface losses from that eigenmode solver can then be used as an input for the thermal analysis, which can include the flow rate of water that's used to cool the cavity. And for this particular example, the conjugate heat transfer solver was used. And again, you can do a particle in cell tracking simulation. In this case, looking at positive carbon ions with a fixed emission model. And they have an initial energy of 60 MeV, and they gain 5 MeV while passing through this 9-cell cavity. As I said, a nice example of a multi-physics simulation. So the last thing I'd like to have a look at is a 3D experience platform workflow. 3D experience includes lots of the different Dassault system tools and allows us to connect them up together. So in this particular example, what I'm showing is we're using some CATIA technology called part design on the 3D experience platform, where I've sketched the pole of a single pole of a quadrupole magnet, so a 4-pole magnet. The tip of that quadrupole pole can be controlled using a spline with various a parameterized spline, and that pole can then be extruded to make the complete quarter pole. That pole geometry can be imported into CST using simply one click from the 3D experience platform, and the rest of the quadrupole built up around it, including the other features relevant for electromagnetic simulation. That simulation can be solved. Key features, for instance, the Fourier components that I talked about earlier. So this is just the radial component of the B field around a circle in the middle of that quadrupole magnet, and we can take a Fourier analysis of that. So you can see the main quadrupole field that we're trying to excite, and then these higher order terms, some of which you can just about see are not zero. So that's what we're looking to improve. And then this whole simulation can be saved back to the 3D experience platform. We can then do an optimization using another piece of technology called Process Composer, where we can attach a CST app as part of this simulation, where the CATIA parameters are available to this optimization, as are the CST outputs. We can then wrap the CST app in a design optimization, where the parameters are given as bounds and the targets can be provided as outputs, and we then allow that optimization to run. And then in another app called Performance Study, we can then do an assessment of these results and plot various of the parameters against their outputs. We can then choose an optimal design and load it back to part design. And again, with one click in the CST, we can upload that CAD and look at the simulation. And immediately you can see that via this optimization, we've reduced the saturation on the pole tips. The templates are automatically generated, and those Fourier coefficients you can see are now all reduced to practically zero. And in an additional step, we've exported these fields to Opera, where we can do a force calculation on the coils and look at an initial sort of coil displacement calculation. And this is something that it would be nice to use some additional Dassault Systems technology in Abacus, which is available on the 3D Experience platform, and my team is working on this process at the moment. So that's the end of my talk. And just to go through a quick summary, we've looked at low energy beams, particle accelerator magnets, RF cavities, wake fields, multiphysics, and then a brief look at how you can use the 3D experience platform in a combined workflow looking at these kind of effects. And I'd like to stop there. So thank you very much. And if anyone has any questions, I'd be happy to answer them.